random variables, but other possible examples beyond that. So this is, for example, independent coefficients. Then we think it seems like the probability that f is reducible divided by the probability that f has a linear factor should go to a constant. And of course, you could object immediately because these green, the cases where the degree was even, did not have linear factors, so this would be dividing by 0. But we said, or smallest degree. The general theme being that the simplest case should be the dominant contribution to factoring. And this was this limited. This limit would be as the degree goes to infinity, or support of the coefficients goes to infinity, or both. In the cases that the students studied over the summer, it seems to be very robust. And you can observe this behavior in many different models with different kinds of randomness. A number of models that we worked with came from random matrices, and that provides a case where the coefficients are not independent anymore. They're dependent on each other. And so we have, this is a good time. Maybe I'll mention a little bit more about the random matrices. Part of this goes back to my thesis. When I was a student here at Rutgers, this was joint work with Dean Brekken and Van Vu, my advisor. And what we showed is if M is a matrix with plus minus 1 entries, and these are Rademacher, so equal probability, then we're not looking, so you could think this is very different, there's no polynomial here, but I'll show you a relationship momentarily. Then the probability that M is singular is at most 1 over root 2 plus the mole of 1 to the n. And this built on some work of Tao and Vu where they showed a similar bound where this 1 over root 2 was instead 3/4. And it's expected the final answer should be 1/2. And it's the same theme as this. If you have a matrix of plus minus 1 entries, what would the simplest way for it to be singular, to have a dependency among the rows? Maybe 2 of them being dependent, and that should be probability 1/2 to the n. And it could be that's the first 2 being dependent. You could have any pair, so maybe there should be a polynomial factor in here, except you can hide all kinds of polynomial factors in the little of 1 underneath an exponent. And so that's what the little of 1 is doing there. That comes back to life. This result, so the idea, I mentioned this result here, this result of, result of mine with Sean Rourke. We use this result to say something about polynomials. So this maybe it's a corollary of this method, of the method we had. So this is O'Rourke and Wood in 2017. We could show that if you looked at the characteristic polynomial of this kind of matrix, and of course that shouldn't shock you too much because this singularity is talking about whether the 0 is an eigenvalue, which is saying that the characteristic polynomial had a 0 as a root. Using a generalization of this theorem, we could show that the characteristic polynomial of the same matrix M is unlikely, so the probability is low, to have small degree factors. To have factors of degree up to, now of course if you got degree up to, this, I guess I'm thinking of this as an n by n matrix. That's why this has the power of n there. And so if you could get up to degree n over 2, you'd be done, because something has to be n over 2. And we could not get up to degree n over 2 but could get a step in that direction up to, let me try to get this right. Up to degree e to the 1/2 minus epsilon. So epsilon here is a constant, but square root b, not all the way to d over 2. And so that still suggests you're likely to see irreducibility, and maybe also suggests that, and I guess this would necessarily suggest, but there's still this heuristic that the way you expect these things to factor would be actually exactly when it's singular. That's one way it will factor. It's very unlikely, but that, the data the students produced supports, though they couldn't produce quite as much data because once you have an n by n matrix, you're sampling. I guess the reason is if you want to study singular plus minus one matrices, you have to sample a lot of matrices, right? You have to sample exponentially many to see on average your first one. And so their data is not as robust, but it does suggest that the dominant contribution of factoring is exactly this, and that the matrices, the characteristic polynomials that factor where the matrix was not singular at the beginning is a vanishing proportion of the total number of factoring matrices there. So that's another thing. And the idea, the reason this works, why is it? This is an interesting case because the characteristic polynomial now, if you think of that the characteristic polynomial, each coefficient comes from these some sub-determinants of the whole thing. Or you could think of it as each coefficient is a symmetric function of the eigenvalues. So there is dependency among them. But the key idea that we use, we call this delocalization. And namely, what that says is that the probability that a polynomial, if you look at the maximum over all complex numbers omega, of the probability that omega was a root, that should control factoring, at least for small degree factors. And the advantage there is that then when you take this kind of delocalization result is known for matrices. And in fact, for eigenvalues of random matrices, stronger things than this are known about delocalization, but you can use any of those delocalization results to turn it into a no low degree factors result about the characteristic of polynomials. So that is where the students got to, and I guess you saw the heuristic. And so when I was preparing this talk, I got an email from the same Sean O'Rourke, and he said there's an interesting paper up on the archive, and it proves the Leibniz-Gokunin, not quite in full. It proves it, assuming the Riemann hypothesis. So it's kind of cheating, but I did, it was October 31st. I was out trick-or-treating, I guess, but someone was submitting papers to the archive, so that's when it came out. And one thing it does, though, it provides possibly a window into what these factoring types really look like. So we've seen this idea that it should be the linear factors controlling what's going on, and maybe this idea, I guess I just erased it, that the probability of a root being taken is what should control the probability of small degree factors. And the result that they came up with is really very nice. I mean, yes, it assumes the Riemann hypothesis, but it says a lot about the structure of the polynomials. And so let me write what they have here. So this is October 31, 2018, and it's by Emmanuel Brulère and Peter Argue. I may well be mispronouncing those names, but that is the right spelling. They work with more general polynomials. So let P be AD, X to D, all the way down to A1. And the AI are independent in integers. And there's some other conditions. They're nice in a few small ways, but one of the interesting ones is that they're also bounded. And they're bound e to the d to 1/10. So it doesn't seem like much of a bound. But they do say in their paper, which I think is quite interesting, that their method does seem to need this bound. So, and it's interesting because if you're talking about irreducibility, which is part of what they're studying here, in Hilbert's irreducibility theorem, having these be very, very big made the problem simpler. And so it's interesting that this is needed here, though maybe because of the quality of the data. So let me get the Riemann hypothesis assumption true. So if generalized Riemann hypothesis holds, and they can specify more specifically which number field it should hold for, but I will just say, assume everything we possibly need. Then this probability 1 minus a very small error, e to the c root b over log b. This polynomial p is equal to capital Phi times p tilde. And what is special about these? P tilde is irreducible. So there is some irreducible part. And capital Phi, this is a product of x to some power. So that says this is kind of the cases where the constant coefficient was 0. That's where we get the power of x's, or the first few coefficients were 0. And cyclotomic polynomials. One thing notable about this is that, so cyclotomic polynomials, these are polynomials that are irreducible, where all the roots are roots of unity, and the first two of them are these, which we've seen before, right? Those are exactly what we saw here. And so what's interesting to me about this, this is the statement here. What's interesting to me is this really does quantify, given the Riemann hypothesis, what's going on with the loaded refactors. You do expect to generally see a large irreducible part, and then a small part based on these cyclotomics, and also x to the n. And I say a small part. They actually have a more detailed result that, in fact, says where they can do a counting argument and study how likely it is that these cyclotomics show up. I will mention Carnyagin's result. Two things about that from 1999. That was the one that provided the first bound of Leak's opinion. This is also not conditional on the Riemann hypothesis. His result also proved the load refactors result, but it produced a very robust there are no load refactors result. And what was interesting is part of his work, he also considered the cyclotomic case and non-cyclotomic case was important. So one of his lemmas or sub-propositions inside that paper is that the probability that P is divisible by any cyclotomic is at most big O of 1 over root d. And if you think back to the previous picture I showed you with zero polynomials, this term is from the probability that it's divisible by x plus 1. So that's one of that's the cyclotomic. And so it was interesting because the cyclotomic case came up in the Carnyagin's work, and that was a critical part of what was going on here. And so this, you could think, okay, is this the end for the experimental approach to these polynomials? Because now, you could have imagined a different RU that would have done statistical analysis and deduced that this had to be true, that when you saw factoring, the factoring, when you saw factoring, it would happen, it would come about because of these cyclotomics. But I think there's still an interesting way forward here, and that is this big question that remains, and this leads back to the original question of Hilbert's irreducibility theorem. What about big coefficients? Right, this result has this condition here. The coefficients have to be bounded by something. They, Rutgers and Rutgers say that this 1/10 is not so critical. You could change that to something else and still have the same kind of result. But they did seem like the result needed some kind of bound on the size of the coefficients in terms of d. And yeah, so you could still ask, what about big coefficients? Could you do statistical analysis and check, do you still have this importance of cyclotomics, or does that dissipate? And that's my alarm, so I'm going to stop there. Thank you.
Experiment you talk. We have 3 minutes for questions. So how is it related to the statistical projector?
So
there was 0 and 1, and now
yeah. So actually, this their result. You could say the A's. The nice includes 0, 1, and then setting the. I guess this should be A0 at the bottom. The niceness includes at least Lapunen's conjecture coefficients, and they do an argument of their own. But this result in Yagin's, you could combine here and say that the cyclotomic part is bounded and goes to 0, and so that moves down there. They have something better where they actually show this heuristic that Sean and I were using that it should be the probability of having a root is what should matter, and they can do that explicitly in this Riemann hypothesis assumed case and show the first 2 terms of the expansion that in fact the probability is first that a linear factor, second a quadratic cyclotomic factor, and get around that way. So they do have that in the case as well. I'll just highlight one tiny thing. This had 2 roots, and up here you had 1 root. And if you check these numbers, you roughly square to get down, which is exactly what you'd expect from a heuristic. So if you're from a linear to quadratic, the blue line to the peaks of the mean, it's square. It's pretty robust there.
is anything known about multivariable?
Yeah, I think so. There is more known there. The Barry Sarkar and Kozma have a result about multivariate polynomials and when they factor, and I think the result was stronger there. They have this large box 1 to 210 coefficients, and I think they could prove more in the case when it was multivariate. Maybe the additional degree of freedom allowed the proof method to work better.
And so final phase is different.
Yeah, it's completely different. Usually you can factor everything. The irreducibles are rare, and it's if you read into the dominant foot far enough, they have the exercise or developed over a section of how you can count. You can just count all the irreducibles up, and that's not very many of them.
Thanks for that again.